So welcome to the series on pure math for physicists. So the objective here is not to see all the results that we are going to do in the pure math topic, that we are going to see all the theorems and all the main results in the pure math topics that we are going to see, but to merely understand the terminology. So that's that wherever you see the results that are being used, so these are pure math topics which are starting to have applications in different areas. Okay, so they're not full-fledged, so that's why they are called pure, right? So they're not full-fledged, they don't have applications as much as we see in the other areas of mathematics that we come across in your regular physics. But there are few topics like topology being starting to being used in physics, like we have topological field theory. Okay, and then we have algebraic geometry, so they are also being used in string theory. Okay, so we'll see what these things mean. Okay, so merely to understand the language of pure mathematicians, so that when you come across them in physics, the language is not alien to you. So that's the main objective, right? So what is a ring? So we've already seen what is a group. Okay, so what we're dealing with is abstract algebra. Okay, so these are topics covered in abstract algebra, and we've already seen what is a group. So with previous videos we've done what is a group. So a ring, so what is a ring? So just like where we said uh, some objects or elements are, they form a group when they satisfy certain axioms. So similarly, a ring is formed when certain axioms are satisfied. So a non-empty set R is a ring if it is closed, if it has two closed binary operations, that is addition and multiplication. Okay, so what is closure? You already seen in groups, right? Closure means that when you perform the operation and you get the result also belongs in the set R. Okay, that is what closure means. So here the results must be closed under additions and multiplications. That is the ring axiom. Okay, so here first two axioms, you have addition, and it must also have a unit element, right? So you know what is a unit element. You take any element, you perform the ring operation with it, you must get the result. So the group element here is 0. Okay, so you take 1, so we're just seeing an example. 1 added with 0, it gives you the element itself. That's the unit element, right? So that is the unit element. Okay, so this is an example. So this is called abstract algebra because here we are going from example to these abstractions. Okay, so that's why it's called abstract algebra. So when you see it so abstractly, you won't get it, right? Because it's too abstract for you. But all our abstractions actually come from all these kind of examples that we see in examples that we come across. So from the examples we go to abstractions. So we have similarly for multiplications these three axioms that they are. So here we have the three axioms. So you can see what the axioms are. One is nothing but the commutativity, right? Commutativity and associativity, right? So here, if a plus b is also equals to b plus a, and here we have the associativity property, right? How you group the terms, that is the bracket operation. So similarly, here we see it is the addition operation. Similarly, these axioms must be satisfied for multiplication, then it is the ring, right? So just describing what we have said here so far. So it should be, there is a unit element and it is a commutative, and it should be associative. So when it is commutative, it is called a field. There is a special terminology. When the commutative property is satisfied, it is called a field. When the commutative property is satisfied, it is called a field. Okay, and when a commutative ring has an identity along with it, it is called an integral domain. Okay, so just seeing more terminologies. As I said, this course is to introduce the language and the terminology, so that when you come across it in different areas of your study, you will know what's happening. And it's called a division ring, where you can perform division. Okay, so it is a division ring where you can have division operations. And a field E is an extension field of F if F is a subfield of E. Okay, just like you have subgroups, right? Just like you have subgroups, just like you have subset, you have a subfield. Okay, the field F is called the base field. Okay, so just introducing some terminology. So here you have it written in the form of a subset notation. Okay, so F subset E. So here you can define a polynomial over a ring. Okay, so you can define a polynomial over a ring. Here the elements a naught, a1, a2, and a3 goes to an belong to the ring. We've seen what is a ring already, right? And a polynomial is called a mononomial. Okay, monomial when the first element is equal to 1. Okay, the first leading term is equal to 1, and it's called a monic. Okay, it's called a monic, and the degree of the polynomial is the highest, the leading order. Okay, so here we have, if it goes up to, let's say the polynomial term goes up to x5, then the degree is n 5. Okay, the degree is 5. So just like we can define polynomials over a ring, we can also define a vector space over a ring. Okay, so here we have F is a field. So remember what we said is a field. It is a commutative ring with a identity, right? It is a commutative ring with an identity. So we can define a vector space over a ring, and these are the elements of the vector space. So this is nothing but something like when we write. So these are the examples from which we go to abstraction. So when I write 3i plus 3j, the I and the j are the vector space elements, and here 3 and let's say we'll keep this element as 4. Okay, so 3 and 4 are the elements of the ring. Okay, so they must satisfy these axioms. Okay, so F is the alpha, alpha, beta are all elements of the field or the commutative ring with the identity, and here we have V. Okay, V is the element of the vector space. We can have more elements, U, V, how many ever elements of the vector space we have. So here these are I and J specifically. Okay, so this is the example, this is the abstraction that we go to, and we can generalize the generalization or the further abstraction of a vector space is a module over a ring. Okay, so this is higher generalization or a higher abstraction of a vector space. It's defined as a module over a ring. So we know that these I and J are linearly independent. What does linearly independent mean? You cannot write one in terms of the other, right? Because to span a two-dimensional space, you need both x and you need both x and y axis, right? To span a two dimensions, you cannot write one in terms of the other. So they are linearly independent. But if it happens to be that you can write one in terms of the other, supposing I pick another basis vector, let's say like this, let's call this vector a, but this a can be written in terms of x and y, because this will be the x component, right? So this a is going to be some component of x and some component of y. So this is not linearly independent, right? So when you pick a basis, right, or when you pick a basis element, or when you pick the elements of the vector space, if they are linearly independent, that means you cannot write them as linear combination of one another. Okay, you've already seen these things in your in a applied mathematics. So here we generalize them. So we call them as spanning, right? So when you can span a vector space, a two-dimensional vector space can be spanned with the elements I and j, right? The elements I and j, the unit vectors of x and y. So they are linearly independent. But if they are linearly dependent, then they can be written in terms of one another. They can be written in terms of one another. Okay, so that brings our the abstract algebra terminology that I wanted to introduce to a close. Next, we'll start with topology. Okay, so I'll meet you then.